All right, so let's get started with some basic examples of doing the substitution rule, or as it's also known, u-Substitution. All right, so let's start with, say, computing the integral of something like sine of 3x dx. Okay, so this is a type of integral that after you've kind of done a few, you won't really use u-Substitution on this anymore. But to technically do it, you do have to use it. So how do we figure out how to apply u-Substitution to this? Well, what we want to do is we want to look for something that's like a composition in the function, right? We want to look for a part that has an inside to it. In that case, the inside here would be 3x and the outside function would be sine x here. So what we're going to do is try out saying u equals 3x, and then du is going to be 3dx. Right? Now we have to get all of the x's in this integral swapped over to u's. So, all right, if we sort of get started with that here, right, the 3x here obviously turns into u, but the question is, what happens to this dx? Well, we need to swap out the dx, and we have a dx here, but there's this pesky 3 here. But that's fine, because we can just take this and move it over. So if we divide by the 3, then we have dx by itself. And now we can write in 1/3 du. All right? So I'm going to take this 1/3 and I'm going to pull it all the way out of the integral here because constants are annoying to have in the way here. So 1/3 integral sine of u du. And we know how to integrate sine. That's negative cosine. And remember, plus c. Okay. And now we want to make sure our final answer should be in terms of x. So we should take this u and swap it back here for the 3x. So I'm going to pull out this negative sign. So negative 1/3 cosine of 3x. Right? And then plus 1/3 times c. Well, 1/3 times an arbitrary constant, still arbitrary. So we'll just say c. And that's it. All right? So that's how we can start attacking stuff like this. Let's look at another example. Something like x e to the x squared dx. All right? So this thing, again, once you've done lots of u-Substitutions, this will feel a lot more kind of obvious, and you can probably do it without doing the substitution. But at this point, let's stick with using it. So what we want to do here is we want to say, well, what part of this looks like it's an inside, or function with an inside and an outside? What part of it looks like a composition? Right? That's this part right here. This part looks like a composition. And the inside of that composition appears to be the x squared here. So we're going to say, well, u equals x squared. Okay? If we do that, then we need to make sure that we're able to fit du into this integral. So take du, that's going to be the derivative here, which is 2x, and then times dx. Right? It's very important that we have this dx here because it has to replace this dx. All right, so how can we get this expression in here? Well, we know this u equals x squared is going to take care of this bit. We have this extra x, oops, wanted to use red there. We have this extra x dx floating around. Well, we have an x dx right here, but there's this extra 2. But just like last time, that doesn't actually pose an issue. We just divide by that 2 and we're left with x dx. So this integral here, we can swap out to be e to the u. That's the blue part. So actually, let me write that in blue. Right? So e to the u times the x dx turns into this 1/2 du. Great. Now let's go ahead and compute this integral. So I'm going to pull out that 1/2 just to make this look a little bit nicer. And now it's turned into one of those basic forms that we know how to integrate. So 1/2 integral of e to the u is e to the u plus c. And now I'm going to distribute that 1/2 and I'm going to replace the u with the x squared. And remember, 1/2 times an arbitrary constant is still arbitrary, so we stop there. And that's it. So those are a couple examples of using u-substitution on some basic integrals. To close this out, let's find the antiderivative of a type of, or of a function that's one of our basic functions, right? That doesn't show up as the derivative of something else. Right, so I want to end with integrating tangent of x. Right? So this function here is one, we don't have a function whose derivative is tangent, right? We know the derivative of tangent is secant squared, but it would be really nice if we knew the integral of tangent as well. So what we're going to do here is sine of x over cosine of x dx, because that's what tangent is. And remember, this is how we did the derivative of tangent. We split it into this and did a quotient rule. So we still want to split this up here for the integral, but now, now we need to be able to integrate this, and we're going to use u-substitution. So what we need to figure out here is, how do we get a u in there so that du shows up? Well, it's a little bit tricky here, but in this case, when we're trying to think of the inside part of a function here, we also want to look at, well, what part is most difficult to deal with inside the integral? The sine on top, not so much. The cosine on bottom, a little more troublesome. So we can view this integral as 1 over cosine x times sine x dx. Now, if we look at it this way, we have kind of 1 over t, and 1 over t is the outside function, and cosine x is the inside function. So let's try that out. We're going to try out u equals cosine of x. Right? Whenever we're picking u, we want to see, at least put some thought into, is the derivative of u sitting around here? Right? In this case, we know du is minus sine of x dx. Actually, I don't need that parentheses. And, well, we have this the sine x dx, and we have sine x dx here. So we're going to be able to do this integral. So 1 over cosine x, that's going to be 1 over u. Sine x dx, I need to move this negative to the other side, and we're going to get negative du. All right. So now we integrate this. All right. So let me just maybe put the negative out here, 1 over u du. All right. Remember what the integral of this guy is. This winds up being negative ln absolute value of u plus c. And then we just pop the u back in there. Negative ln of cosine x plus c. So this is a perfectly acceptable form of the answer. A typical way you see this is this answer, ln of secant of x. plus c. This is another way you can see this answer written sometimes. And the way you see that is this negative sign out here. It comes in as the exponent up here. So you have cosine of x to the minus 1 power, which means 1 over cosine, which is secant of x. All right? So just to write it on its own line here, tangent of x dx is equal to ln of secant of x, absolute value, plus c. All right, so try out something like integral of cotangent. Okay? Hope you enjoyed.